Hello, this is Richard Collins, your instructor in ATM101 Weather and Climate of Alaska at the University of Alaska Fairbanks. Welcome to Unit 2, the Atmosphere, an Ocean of Gases. Today I want to highlight the fundamental ideas that we will be exploring in Unit 2. The story of desert dust reminds us that the atmosphere and the surface of the Earth are connected. Dust from deserts is also transported across the Pacific from Asia to Alaska and made headline news in 2008. In 2011, Alaskans were concerned about how this transport might carry nuclear material released from the nuclear reactors in Japan to Alaska. In this unit, we're looking at the question, what is the composition and structure of the atmosphere? And this slide lays out several of the key themes associated with answering this question. The composition of the atmosphere has varied since the formation of the Earth and continues to evolve today. Variations can be due to geological events where gases are released into the atmosphere from the Earth, the most spectacular example associated with volcanoes. However, one of the great questions of our day is the steady rise in carbon dioxide, a so-called greenhouse gas. In carbon dioxide observations, we see a long-term steady rise associated with the burning of fossil fuels, as well as a yearly variation associated with changes in plant growth with the seasons. The atmosphere is 99% nitrogen and oxygen. Oxygen both supports life and is created by living things. However, the importance of a gas is not just about how much of it there is. Minor gases matter a lot. Water, carbon dioxide, and ozone are all minor gases in the atmosphere that are critical for maintaining life on our planet. The scientific method is rational, even if scientists are not. The story of the ozone hole is one of the great scientific detective stories in atmospheric science that illustrates the scientific method. When the hole was first discovered, many scientists thought that it was an error in measurements. The ozone hole is shown here on this map of the southern hemisphere as the pink region over Antarctica of low ozone. The hole did not agree with existing understanding about ozone, which predicted high levels of ozone in polar regions. These green levels of ozone are high, and our theories at the time were that the whole Antarctic region would be green with large amounts of ozone over Antarctica. The educated guess that turned out to be right was that chlorine, which had been building up since industrial times in the atmosphere, was interacting in Antarctica with ice clouds that were particular to the polar region and therefore creating conditions for the destruction of ozone. This educated guess required new observations and new experiments so its hypotheses could be tested rigorously. The educated guess or insight came from a group of scientists who had been immersed in studying the chemistry of ozone. While it took a while for other scientists to accept it, the evidence eventually stacked up in its favor and proved the hypothesis of chlorine-activated destruction of ozone to be right. A model is a tool for understanding. A model, as defined here, a cheaper, simpler version of the real thing, might make you pause if you've ever been described as a model spouse or a model partner. Models are fundamental tools in how we understand the atmosphere. The Earth and atmosphere is big, and we don't have one version. We only have one version of it. We don't have multiple planet Earths that we can look at and see what's happening on them. Also, we cannot turn off elements of the atmosphere and Earth to test ideas. We can't come in one day and say, let's stop all the rainfall for a month and see what happens. It's not an option. However, sometimes we do get events that allow us turn things off, and one such example is after 9/11, when commercial aircraft were grounded and scientists did use it as an experiment to see if cloud patterns changed due to the lack of aircraft contrails. We monitor the atmosphere from weather stations and the launching of radiosondes. The map on the right shows the distribution of radiosonde stations across North America, and the map on the left shows the distribution of surface stations in Alaska. As regards the radiosonde stations, take a look at how few stations there are in Alaska and northern Canada, and even within Alaska, how few there are in central Alaska. As you look at this distribution of stations, think about the pressure maps of weather systems that we looked at in Unit 1, and think about the typical size of a high or low pressure system. As such a system passes over North America, how many radiosonde stations will it pass at one time where we can get multiple measurements of the high and low pressure system and try and understand and predict its behavior? As we look at the surface stations in Alaska, you might want to think about the fact that as you make your measurements locally this semester, each of you is adding to the network of surface stations in our state. The temperature of the atmosphere varies with height, and we divide the atmosphere into a set of regions based on those temperature variations. The ground tends to be warmest. Not always during an inversion in Fairbanks at -40, but in general the ground is the warmest part of the atmosphere. The atmosphere cools with height in the troposphere up to the tropopause. The atmosphere warms with height in the stratosphere due to sunlight being absorbed in the ozone layer and giving up its energy to heating the atmosphere in the ozone layer. At the stratopause, the atmosphere then cools again in the mesosphere. And finally, beyond the mesopause, the atmosphere warms again in the thermosphere. The warming in the thermosphere is due to interactions between the Earth's atmosphere and the solar wind out there at the edge of space. It's not direct heating as we think about it lower in the atmosphere. The presence of the aurora reminds us that the upper atmosphere has unique characteristics and hosts unique processes. The name ionosphere reflects the fact that this region of the atmosphere is ionized, having electrically charged atoms and molecules called ions. Remember that our Sun is an unshielded nuclear reactor and emits a continuous stream of electrical charged particles called the solar wind. The solar wind interacts with the ionosphere and can cause changes that disrupt radio communications, which can play havoc with our global navigation systems, increasingly important in the age of GPS, where we're using positioning systems for all types of navigation. The aurora is also formed as part of this interaction, and the different colors of the aurora, here red on top and green lower down, indicate interaction with different gases in the atmosphere as particles penetrate deeper into the atmosphere, collide with gases, and create the light that we see in the aurora. Some closing thoughts and summary of the points that we've looked at in this unit. A lot of what we've said can be summed up, I think, in the contrast from a picture taken from the moon looking back at the Earth. The moon, our closest neighbor in space, has no atmosphere and is generally a dry and lifeless place. If you look back at the Earth with its atmosphere, what we're really seeing is the troposphere with its clouds and weather and the land systems below it. The Earth's atmosphere is in balance with the planet and maintains life on our planet. It is a complex system that can be full of surprises. It's a major challenge to understand the weather and climate and requires a systematic approach in observations, modeling, and understanding.